There are several potential problems with using hospital-grade alternating current in normal office environments. Firstly, electromagnetic interference or EMI. Hospital-grade alternating current units are designed to minimize EMI, which can interfere with sensitive medical equipment. This level of protection is often unnecessary in a normal office environment. Secondly, cost. Hospital-grade alternating current units are typically more expensive than standard units. Thirdly, overkill. Using hospital-grade equipment in a non-hospital setting may be excessive and unnecessary. Fourthly, confusion. Using different grounding methods for different circuits can lead to confusion and potential safety hazards in the future. Fifthly, code compliance, specifically regarding isolated ground. The use of insulated green wire for isolated ground is not permitted by the National Electrical Code, or NEC, for normal office receptacles. The NEC requires equipment grounding to be provided using a continuous bare or insulated green or yellow wire. A green wire alone is not permitted. For normal office environments, it is generally recommended to use standard alternating current units. They provide adequate cooling and do not pose any significant EMI risks. It is also recommended to follow NEC grounding requirements, using a continuous bare or insulated green or yellow wire for equipment grounding. Maintain consistency by using the same grounding methods throughout the office to avoid confusion and ensure safety. There may be specific situations where hospital-grade alternating current units or isolated grounding are necessary in an office environment, such as offices within hospitals or medical clinics which may require hospital-grade equipment, or if there is a critical need to minimize EMI. In certain cases, the NEC allows for deviations from the standard grounding requirements, but this must be approved by the local electrical inspector. It is important to consider all of these factors before deciding to use hospital-grade alternating current units or isolated grounding in a normal office environment. Let's delve a little deeper into the specific code requirements and potential issues associated with grounding in an electrical system. Grounding serves two primary purposes. Firstly, to protect people from electrical shock by providing a low impedance path for fault current to flow back to the source, tripping a circuit breaker or fuse and disconnecting the power. Secondly, to minimize electrical noise and interference, ensuring the proper operation of sensitive electronic equipment. The NEC outlines specific requirements for grounding and bonding to achieve these goals. A key concept is the equipment grounding conductor, or EG. This conductor provides the low impedance path for fault current. As previously stated, the NEC mandates that the EGC be a continuous bare or insulated green or yellow wire. The purpose of the green or yellow insulation is to clearly identify the wire as the equipment grounding conductor, preventing it from being used for any other purpose. Using only a green wire without the yellow stripe is technically not permitted as an equipment grounding conductor according to the NEC. The NEC also addresses the use of isolated grounds, or IGs. Isolated grounds are sometimes used to reduce electrical noise in sensitive electronic equipment circuits. An isolated ground receptacle has a grounding terminal that is isolated from the metal parts of the receptacle and the building's grounding system. The isolated ground conductor is run directly back to the electrical panel's grounding bus, without being connected to any other grounding points along the way. While isolated grounds can be effective in reducing noise, they must be installed correctly to avoid creating safety hazards. The NEC permits the use of isolated grounds under certain conditions, but it does not allow the use of an insulated green wire for the isolated ground conductor in normal office receptacles. The NEC also requires that the isolated ground conductor be the same size as the circuit conductors. When considering the use of hospital-grade alternating current units, it is important to understand their specific features and benefits. Hospital-grade alternating current units are designed to meet stringent requirements for safety and reliability. They typically include features such as redundant power supplies, surge protection, and EMI filtering. These features are intended to protect sensitive medical equipment from power outages, voltage spikes, and electrical noise. However, these features also add to the cost and complexity of hospital-grade alternating current units. In a normal office environment, the risks of power outages, voltage spikes, and electrical noise are typically much lower than in a hospital. Therefore, the benefits of using hospital-grade alternating current units may not outweigh the costs. In addition to the specific code requirements for grounding and the features of hospital-grade alternating current units, it is also important to consider the overall electrical system design when making decisions about grounding and equipment selection. The electrical system should be designed to minimize the risk of electrical shock, fire, and equipment damage. It should also be designed to provide a reliable and stable power supply for all of the equipment in the office. This requires a thorough understanding of the electrical loads, the wiring methods, and the grounding and bonding techniques. It is also important to consider the potential for future expansion or modification of the electrical system. The electrical system should be designed to accommodate future changes without compromising safety or reliability. A qualified electrical engineer or electrician can help to ensure that the electrical system is properly designed and installed. It can also provide guidance on the selection of appropriate equipment and the implementation of proper grounding and bonding techniques. Remember that the NEC is a minimum standard. It is always permissible to exceed the requirements of the NEC as long as the installation is still safe and reliable. However, it is never permissible to violate the requirements of the NEC. Ignoring the code can create dangerous situations. When making decisions about grounding and equipment selection, it is important to consult with a qualified electrical professional and to follow all applicable codes and standards. This will help to ensure the safety of the occupants and the reliability of the electrical system. Let's examine some practical examples to illustrate the potential problems of improper grounding and the benefits of following NEC guidelines. Imagine an office building where the equipment grounding conductor is not properly connected. A fault occurs in a piece of equipment, such as a computer, causing the metal chassis to become energized. Because the equipment grounding conductor is not properly connected, there is no low impedance path for the fault current to flow back to the source. As a result, the circuit breaker does not trip, and the metal chassis remains energized. An employee touches the energized chassis and receives an electrical shock. This scenario highlights the importance of a properly installed equipment grounding conductor. Now consider an office building where isolated grounds are used improperly. The isolated ground conductor is connected to a metal water pipe along its path back to the electrical panel. This creates a ground loop, which can introduce electrical noise into the system. The electrical noise can interfere with the operation of sensitive electronic equipment, such as computers and audio equipment. This scenario illustrates the importance of properly isolating the isolated ground conductor. Conversely, let's consider an office building where the electrical system is designed and installed in accordance with the NEC. The equipment grounding conductors are properly connected, providing a low impedance path for fault current. The isolated grounds are properly isolated, minimizing electrical noise. As a result, the occupants are protected from electrical shock and the electronic equipment operates reliably. These examples demonstrate the importance of following NEC guidelines for grounding and bonding. Proper grounding and bonding can protect people from electrical shock, minimize electrical noise, and ensure the reliable operation of electronic equipment. Another critical aspect of electrical safety is arc flash protection. Arc flash is a dangerous electrical explosion that can occur when a fault current flows through the air. Arc flash events can generate extremely high temperatures, intense light, and pressure waves. These hazards can cause severe burns, blindness, hearing loss, and even death. The NEC requires that electrical equipment be labeled with arc flash hazard warnings. These warnings provide information about the potential arc flash hazards and the personal protective equipment, or PPE, that is required to work on the equipment safely. Employers are responsible for providing arc flash training to their employees and for ensuring that they have the proper PPE. The PPE typically includes items such as flame-resistant clothing, safety glasses, and gloves. It is important to never work on energized electrical equipment unless you are properly trained and equipped. Energizing the equipment is always the safest option. In addition to arc flash protection, It is also important to be aware of other electrical hazards, such as shock and electrocution. Shock can occur when a person comes into contact with an energized electrical conductor. Electrocution can occur when a person receives a lethal dose of electrical current. To prevent shock and electrocution, it is important to follow safe work practices such as wearing rubber gloves and using insulated tools. It is also important to inspect electrical equipment regularly for damage. Damaged equipment should be repaired or replaced immediately. Always treat electricity with respect and follow all safety precautions. Electricity is a powerful force that can be dangerous if not handled properly. By following safe work practices and being aware of the hazards, you can protect yourself and others from electrical injuries. Continuing on the topic of electrical safety, let's discuss the importance of regular electrical inspections. Regular electrical inspections can help to identify potential hazards before they cause problems. A qualified electrical inspector can identify overloaded circuits, damaged wiring, and other electrical hazards. The inspector can also recommend corrective actions to address any problems that are found. Electrical inspections should be performed on a regular basis, especially in older buildings. Older buildings may have electrical systems that are not up to current standards. The electrical inspector can help to identify any deficiencies and recommend upgrades to improve safety. It is also important to have electrical inspections performed after any major renovations or modifications to the electrical system. This will help to ensure that the electrical system is still safe and compliant with current codes. The frequency of electrical inspections will vary depending on the type of building and the local regulations. However, it is generally recommended to have electrical inspections performed at least every 3 to 5 years. In addition to regular electrical inspections, it is also important to have a preventative maintenance program for electrical equipment. A preventative maintenance program can help to extend the life of electrical equipment and prevent breakdowns. The preventative maintenance program should include tasks such as cleaning electrical equipment, tightening connections, and testing circuit breakers. The frequency of preventative maintenance will vary depending on the type of equipment. However, it is generally recommended to perform preventative maintenance at least once a year. Proper electrical safety practices are essential for protecting people and property from electrical hazards. By following safe work practices, being aware of the hazards, and having regular electrical inspections and preventative maintenance, you can help to ensure the safety of your electrical system. Let's now explore the specific requirements for electrical panels and their proper installation. Electrical panels, also known as circuit breaker panels or load centers, are the heart of an electrical system. They distribute electrical power to various circuits throughout a building. The NEC sets forth specific requirements for the installation and maintenance of electrical panels to ensure safety and reliability. Firstly, electrical panels must be installed in readily accessible locations. This means that the panel should not be blocked by furniture, equipment, or other obstructions. The panel should also be located in a well-lit area so that it is easy to see the circuit breakers. Secondly, electrical panels must be properly grounded. The grounding conductor must be connected to the panel's grounding bus and to a grounding electrode, such as a ground rod or a metal water pipe. This grounding system provides a low impedance path for fault current, protecting people from electrical shock. Thirdly, electrical panels must be properly labeled. Each circuit breaker must be labeled to indicate the circuit that it controls. This makes it easy to identify the correct circuit breaker when troubleshooting electrical problems. Fourthly, electrical panels must be kept clean and dry. Dust, dirt, and moisture can damage the circuit breakers and other components in the panel. The panel should be cleaned regularly with a vacuum cleaner or a damp cloth. Fifthly, electrical panels must not be overloaded. Each circuit breaker is designed to protect a specific circuit from overcurrent. If a circuit is overloaded, the circuit breaker will trip, interrupting the power to the circuit. It is important to avoid overloading circuits by using too many appliances or devices on the same circuit. Sixthly, electrical panels must be inspected regularly. The inspection should include checking for loose connections, damaged wiring, and signs of overheating. Any problems that are found should be corrected immediately. 7th, electrical panels must be installed in accordance with the manufacturer's instructions. The manufacturer's instructions provide detailed information about the proper installation and maintenance of the panel. Following these instructions will help to ensure that the panel is installed safely and reliably. By following these guidelines, you can help to ensure the safety and reliability of your electrical panels. Electrical panels are a critical component of an electrical system, and their proper installation and maintenance are essential for preventing electrical hazards. Moving on to another important aspect of electrical systems, let's discuss surge protection. Surge protection is designed to protect electrical equipment from voltage surges, also known as transient voltages or spikes. Voltage surges can be caused by lightning strikes, power outages, or other electrical disturbances. These surges can damage or destroy sensitive electronic equipment such as computers, televisions, and appliances. Surge protection devices, or SPDs, are designed to divert voltage surges away from electrical equipment. SPD are typically installed at the electrical panel and at individual outlets. There are two main types of SPD. Firstly, whole-hour surge protectors, which are installed at the electrical panel and protect all of the circuits in the house. Secondly, point-of-use surge protectors, which are plugged into individual outlets and protect the equipment that is plugged into the outlet. When selecting an SPD, it is important to consider the surge current rating. The surge current rating is the maximum amount of current that the SPD can safely divert. The higher the surge current rating, the better the protection. It is also important to consider the voltage protection rating, or VPR. The VPR is the maximum voltage that the SPD will allow to pass through to the protected equipment. The lower the VPR, the better the protection. SPD should be installed by a qualified electrician. The electrician will ensure that the SPD is properly grounded and connected to the electrical system. SPD should be inspected regularly to ensure that they are functioning properly. Some SPD have indicator lights that show whether the SPD is still providing protection. If the indicator light is off, the SPD should be replaced. Surge protection is an important part of protecting electrical equipment from voltage surges. By installing SPD, you can help to prevent damage to your valuable electronic equipment. Consider now the role of ground fault circuit interrupters, or GFCIs. Ground fault circuit interrupters are life-saving devices that protect people from electrical shock. GFCIs are designed to detect ground faults, which occur when electrical current flows through an unintended path to ground. Ground faults can occur when a person comes into contact with an energized electrical conductor or when there is a short circuit in electrical equipment. When a GFCI detects a ground fault, it quickly trips the circuit, interrupting the flow of electricity. This can prevent serious injury or death from electrical shock. GFCIs are required in areas where there is a high risk of electrical shock, such as bathrooms, kitchens, and outdoor locations. The NEC specifies the locations where GFCIs are required. GFCIs are typically installed in electrical outlets or circuit breakers. GFCI outlets have two buttons, a test button and a reset button. The test button is used to test the GFCI to make sure that it is functioning properly. The reset button is used to reset the GFCI after it has tripped. GFCIs should be tested monthly to ensure that they are working properly. To test the GFCI, press the test button. The GFCI should trip, interrupting the power to the outlet. To reset the GFCI, press the reset button. If the GFCI does not trip when the test button is pressed, it should be replaced. GFCIs are an important safety device that can protect people from electrical shock. By installing GFCIs in areas where there is a high risk of electrical shock, you can help to prevent serious injury or death. The discussion now transitions to the crucial topic of arc fault circuit interrupters, or AFSIs. Arc fault circuit interrupters are designed to protect against fires caused by arc faults. Arc faults are dangerous electrical conditions that can occur when there is a break or damage in electrical wiring. Arc faults can generate high temperatures that can ignite nearby materials, such as wood, paper, or fabric. ASICs are designed to detect arc faults and quickly trip the circuit, interrupting the flow of electricity. This can prevent fires from starting. ASICs are required in many areas of the home, including bedrooms, living rooms, and dining rooms. The NEC specifies the locations where ASICs are required. ASICs are typically installed in circuit breakers. ASIC circuit breakers look similar to standard circuit breakers, but they have additional circuitry that detects arc faults. ASICs should be tested monthly to ensure that they are working properly. To test an ASIC, press the test button on the circuit breaker. The ASIC should trip, interrupting the power to the circuit. To reset the ASIC, move the circuit breaker handle to the off position and then back to the on position. If the ASIC does not trip when the test button is pressed, it should be replaced. ASICs are an important safety device that can protect against fires caused by arc faults. By installing ASICs in areas where they are required, you can help to prevent fires and protect your home and family. The safety topic continues with an overview of tamper-resistant receptacles, or TRRs. Tamper-resistant receptacles are electrical outlets that are designed to prevent children from inserting objects into the slots. TRR have internal shutters that block the slots when an object is inserted unevenly. The shutters only open when a plug is inserted correctly. TRR are required in all new construction and renovations in areas where children are likely to be present, such as homes, schools, and daycare centers. The NEC specifies the locations where TRR are required. TRR looks similar to standard electrical outlets, but they have the letters TR printed on the face of the receptacle. TRR are an inexpensive and effective way to protect children from electrical shock. By installing TRR in areas where children are present, you can help to prevent electrical injuries. To conclude this overview, it is imperative to always consult the latest edition of the National Electrical Code and any applicable local codes for the most up-to-date requirements and regulations regarding electrical installations and safety practices. This information is intended for educational purposes and should not be considered a substitute for professional electrical advice. Always consult with a qualified and licensed electrician for any electrical work.